Okay, so we're gonna finish up with the Bruderer data set today, and then we're gonna switch to also the CelebSec data set. So we're trying to get through 2 data sets, but I want to remind everyone. Let's see. Here we go. So we're dealing with this case where there's been some DDA runs done on pooled sample to build a to build this prior knowledge with which we're going to go back and interrogate these DIA runs. And you don't actually even have to do the DDA runs before you do the DIA runs. You can do them before, after, or during. They just provide, and ideally, if you can do these runs on the same column as these runs, then that's going to make them the most powerful. But you can do them separately. And when we get to the CelebSec data set, they were definitely done separately. I get the sense that the Bruderer runs are done closer in time. And then just the really, I guess, the simple workflow, I've been asked, I wish I had a workflow diagram. So this is really what we're doing, and we're doing it multiple times. You even did this in the sit-down hands-on DIA tutorial, which was you built a spectral library, you got IRT library, normalized IRT. Then you chose your product ions. You chose the ions that you're going to target. So you chose a very limited set in the one that you did while you were as using these tutorial papers. The paper tutorial on your own. You chose product ion targets. Then you imported results. That gave you extracted ion chromatograms, and Skyline does a first cut at choosing the right things out of those files. And then you did an M-profit model, M-profit peak picking. And then we're going to, in this class, we're going to export a report, and we're going to use MS Stats to do quantitative analysis. So that workflow is what we're doing over and over. This is what you did yesterday in the tutorial. We're going to do it again on the CelebSec data set. We just did this part this morning for the Bruderer data. We generated our own spectral library and IRTs. So if you were here at 8 a.m. or even if you showed up by 8:30, we went through using max quant results to generate these artifacts of spectral library and IRTs. But yesterday, we didn't do that. What did we do yesterday? What did we use instead of a spectral library here? We used this thing called an assay library. So that was an assay library generated by Spectronaut. But if there's definitely assay libraries coming out of ETH and the Aerosol lab. So the Pan-Human library is one that we keep referring to. It's a really great public resource. So these are the two main sources, people working with OpenSWAT, people working with Spectronaut. You might get an assay library, they might publish something, they might publish something that produces an assay library, and just like the Bruderer data set, you want to go analyze it. And so you have to ask yourself, do I want to go all the way back to their base search results, their max quant results, or in the CelebSec data set, we're going to see that they used Mascot and Sequest and then rolled it up with iProfit, and we're going to build a library from that. Or do you just want to accept their assay library? So that's a question you want to ask, because Skyline can deal with either one of them. Again, actually the assay library, you also have less choice about the product ion targeting. We just used what was in the assay library, but we did one little tweak. What did we do to the assay library that we got from the Bruderer data set? We didn't just use it straight. We did one thing. What? And then then we went to 6. So we started just like, let's see 10, and I guess we didn't take too close a look at that, but yeah, they ranged from like 3 to 10, and then finally we said, okay, we're actually going to throw out everything that doesn't have at least 6, and we're gonna make sure that everything that had 10 only has 6. It can. It's not. Yeah, I was talking to Roland not Roland. No, I was talking to Oliver Bernhard at Biognosis, and so they do have a Skyline report. It actually, somebody just posted it on the Skyline support board because they were asking about it. So there is a report that will produce an assay library in Skyline, and it was in a recent support request, so maybe I can still even find it. And in their case, there's a lot of well, I've lost it already. There's a lot of support going on. Yeah, so if you get that report, and I think you can get it off the Spectronaut website, then you can produce an assay library, and that's what they'll tell you to do. If you say, oh, I want to use Spectronaut, and you talk to the Biognosis people. If you have some weird search engine that they don't, like you're using Morpheus or something that the Biognosis team hasn't built into their normal support, they'll say, oh, go build it in Skyline, because Skyline serves, there's just about, there's still nothing that we know of right now that we don't support. So there's no known search engine. Every time anybody comes to us with, hey, I've got this search engine, we just say, okay, give us an example of it, and then we build support into Skyline. So Nuno Bandera, who was here earlier in the week, also he's got this product called Massive, or this project called Massive, and he also is using BiblioSpec, the library builder that Skyline created, to build libraries. So yeah, we have become a central point for building libraries. So it's somewhat likely that people who want assay libraries will point you that way. The only other real way of building an assay library, and this because it comes out of the Transproteomic Pipeline, which is a project that Rudy Aebersold started, that the ETH group, this open source group, uses this route. Like I think this is the route this is certainly the route that they were teaching at the ETH DIA course, and it's the route that they use to build like the Pan-Human Library, which is to run it through a tool called Spectrast. So there's this tool, so it's part of the Transproteomic Library. So those are sort of, and then actually Spectronaut obviously can build its own assay library. So that's. I think, so I was just showing earlier this morning, I was showing that sort of the really naive algorithm that I first used to generate IRTs using spec, and so this was my first attempt at getting IRTs for 12 DDA runs. So using DDA, generating IRTs out of DDA is actually pretty complicated because of, so if you missed this morning, we were talking about, this is the problem with DDA. These are all the different aligned times at which I got IDs, all these lines. And you can see that there are lines here. And so if you use a mean, you're going to end up like somewhere over here and say, oh, the peak's right there. And that was what I did, is I first just calculated, all the times that I saw, and I used the mean time, thinking, well, if it's a distribution, the mean will be pretty good. But the problem is that, yeah, you get two IDs here and here, you'll say, oh, the peak is here, which is nowhere near any sort of peak. So I switched to median, and then even, but still you can get better IRTs if you actually go get peaks. So anyway, and then this was actually the library generated at one of the DIA courses for using Spectrast. And it came out like this. And the problem is that, a lot of people, Skyline makes this really easy to look at and really obvious. But other, certainly other tools, it's like, well, everything's within 5 minutes. It's still, these are still usable IRTs, but what you would really like is something like this. And the way I got this originally was by using peak times like this on those 12 DDA runs, but then I was able to fix my algorithm to get something like this from the DDA. So yeah, IRTs especially are, it's not what, it takes a little bit of work, and I can't say for sure, but my sense from talking to Henry Lamb, who's the author of Spectrast, was that he used the simplest algorithm to get IRTs. So I'm not sure that I think, I like to think that I improved how Skyline does IRTs from here to here, and I'm not sure that work has happened in Spectrast, but certainly, Spectrast produces usable results, and I think that Ben's pan-human library is a great example. So, all right. So anyway, so we have these two, and then there's this third thing, this chromatogram library we've talked about, and certainly Encyclopedia produces them, but we're not really going to treat that here. So these are the two workflows that you need to remember. We're basically, just walking you around this many times and showing you how to get through this workflow. But generally, I would recommend that you get really comfortable with this part. That's the completely Skyline native workflow of like, hey, I'm going to build a spectral library out of search results. I'm going to get IRTs out of that, and I'm going to go and do product, and I'm going to choose my own product ion targets. And then if you are working with other people and other tools that produce assay libraries, know that you can do that. And that's what we've done with Bruder. So just to reorient people before we get going. So we should have left off here. How many people didn't actually make it to the point where you have one run imported into this Bruder tutorial document? Some people didn't make it here. Okay, so I'm going to talk about this briefly, but then we're going to just open a different document where I've imported all the results. So here's just one file. Let's see what we can learn from the one file. Certainly we have our IRTs here. Actually, so what I tell people, the most important keyboard command in Skyline is F11 to zoom into the peaks and Shift F11 to zoom out. So first of all, what can people tell me about the chromatograms of the IRTs? If you look at them, you'll notice that they are extracted over what time range? They extend all the way from 0 to 130. So that's a pretty long gradient. And so that's the thing about IRTs, is they're sort of required to be detectable over the entire gradient. You can see that they all stick up quite a bit higher than everything else in that gradient. And if I press F11, I can zoom in and look at the actual peaks. So what I found, part of one of the problems I found is I think that like this may be one. Some of these peptides actually have a fair amount of tailing, which produced this effect, where we got a lot of IVs coming out here. Just because they were injected at a very high concentration, we get tailing, and we keep identifying it way out there. And that when I don't have the peak to look at, if you think about a tool trying to just figure out where is the peak based on a whole bunch of IDs like this, it becomes more complicated. Okay, so and then what else can let's do Shift F11 also. Are these so we know that we go out to 130. If we click on the IRT, you can see that the last peptide we see is at about 100. So that's pretty good gradient coverage, but you know, boy, wouldn't we love to have something out at 110 and 120. But so those all look pretty good. And then let's take a look at some of these other things. So first of all, if you look at this first protein, you can see all the peptides. You can see really nice. If you just select a protein, you can see all its peptides, and you can get what was before we created this graph. Paula Piccati showed something like this in a presentation. I was like, wow, we need to do that. And she called this the protein fingerprint. Because you know, if you collect this again and again, you'll see this same fingerprint. And when something changes in here, you can get a sense of, you know, maybe what Mike was talking about. Wow, you know, this, I always see IYY right here, and it disappeared. What was that? So sometimes things change within a protein, and that can be especially surprising. So let's have a look at this first one. What's the range that's extracted here? You know, it's just yeah, it's a little bit before 106 to a little bit before 116, so it's 10 minutes. How do we get 10? Why are we getting 10 minutes? You'll also notice that Skyline's showing me the predicted retention time is 110.4. Yeah, so we went to our settings, we had transition settings, and we said that in full scan settings, we said use only scans within 5 minutes of the predicted retention time. So the predicted retention time, let's see if you go to view, retention times, regression, score to run. Hopefully this will work. I have not pre-tested this. There it is. Okay, so it worked. So here's the regression. You can see that everything's fairly close to, in this view, it looks fairly close to the regression, but we can now, things look very close to the regression when it's plotted like this. So I really like to look at things by plotting the residuals. So that just shows me how far away everything is from the regression. And unfortunately, I have these things, which I think I can actually get rid of by going. So those are just like missing things. And I only recently realized that there is anything missing. So I need to go look at why we're getting missing things. But I can go edit, refine, remove missing results. And it's going to have to recalculate everything once that's done. We have a lot of points here. Wow, so that didn't really... Why didn't that get rid of that? Huh. Okay, well, we'll just zoom in by clicking and dragging a box like this. And so now you can see it's not, you know, it's a little bit not as pretty a picture. You know, so it's not quite a straight line. You can see that it's actually zigzagging between plus and minus 4 minutes. So there's quite a bit of warping from the IRTs. So those are the original predictions derived from the DDA data. And this is not Skyline's algorithm. This is I mean, now I'm kind of interested to run that MaxQuant library that we created this morning and see whether Skyline's IRT predictions, whether this is, it's hard to know whether this is an artifact of the DDA data or this is an artifact of how their IRT picking it works. But this is definitely, you know, when we run our model, I think we're going to find with these data that retention time turns out not to be a super strong score. And, you know, that's pretty, we only gave it 5 minutes to, so even the decoys are going to fall within this 5-minute range, right? And now we have, and our targets are all over this 5-minute range. So you can see that, like, you know, this is not going to be that strong a score, even though there's a really nice trend here. I guess actually if we use Brian Searle's KDE, where he was talking about running across a ridge, you might have a much stronger retention time score. Let's take a look at what the decoys look like. Did we put decoys in this document? Yes, we did. So we can go ahead and go, we can make the points be the decoys. And it's got to calculate that. So that was all targets. So those are things. So there we go. And wow, that's a really strange. Yeah, there's this going on here, which I don't totally understand yet. This is the first time I've ever looked at this. What? Yeah, but it's actually going outside the 10-minute window, so that, I don't quite understand that. I'm going to have to, but basically, you can see that there's, I don't understand, why is it? Yeah, I would expect this, well, I guess, yeah, I don't understand how it's getting cut off here. So it seems to be getting cut off at 6 minutes, which I don't really understand. I feel like it should be getting cut off at, yeah. So anyway, there's some things to work out, and then I really don't understand what this thing is. But yeah, you can see that they're really quite different, but that is going to be polluted by the fact that that there's so much that there's so much like curvature and bouncing around here. So we have much tighter clustering, but if because we're using all we use in the score is the distance they are from their starting point, right? So we don't have any way of sort of using that tight clustering as a score, and that's why Brian Searle went to the KDE model that he explained. But yeah, so you can learn a lot about these things by looking at some of these plots in Skyline, and it's going to be a lot quicker and nicer to do in this small one replicate document. So you can import some data and get a sense of it. Let's take a look at the peaks themselves. Press F11 and we can get in closer. And so that first one looks pretty nice. Second one, you know, maybe there's some interference on this one transition. And you can pretty quickly go through everything. This is a kind of a weird one, I think. It's not all, we don't have coelution on all of them. It's not super well formed. And it's, the intensity is up to 70,000, so it's not, this also is, you know, there's nothing else better here, but I don't know that I think this is a great representation if I'm really you know, I've got a dot P of 0.44. Here also kind of a mess. But then now these, you know, there are quite a few really nice peaks here. Some interferences. Yeah, so like if we really wanted to do quantification on these, yeah, like, so this is where the idea of refinement and actually sort of go, like, there's no way we're going to go through all of these because there's 58,000 peptides here, but certainly, you can already see that if we're going to quantify this protein by all of the peptides, you know, probably that will do okay. It looks like there's a lot of good peptides, but some of the peptides are going to end up causing us noise, right? So there's a lot of good stuff here. We're probably going to have pretty good times quantifying this as a protein. But if I were actually trying to quantify individual peptides, you know, in a clinical setting, I really would not be satisfied with something like this. This is, you know, maybe this is our target, but these two things really need to be removed because they're not measuring our target. So probably most of the signal here is coming from something else. So anyway, so we're going to go over a little bit like how you can do sort of bulk refinement when we get to the CelebSec data. Okay, so that's enough of that. Let's go, if you have this document, go ahead and save it. And now we're going to switch over to the, we're going to switch over and work on the fully imported document. So the only difference between this, you created this, remember? Everybody at least gave a shot at creating this, and then you imported one file. And now I'm going to give you another document, and the only difference between it is, and your file is that it has a whole bunch of files. It has a whole bunch of files imported into it. So it has the full 24 file data set. Hopefully everybody can get that open on our laptop. So we save it, and then, but before we do that, I'm going to have us open up one file so that we make sure that everybody is on the same page for having the annotations and the report template that we need. So our goal is to get some data to Mina so that we can run MS stats and see what that's like. So what we're trying to do is get through that processing workflow we've described, which is defining targets, importing data, running mprofit, and then export a report. So the first thing we're going to, so go to Open. And if you go to, let's see, if you go to, well, do people have this file? Let's see. I have. Well, what I want is this MS Stats Annotation Stats Guide. Do people have that? Is that still on our flash drive? If not, then I guess we'll just have to do without it. I mean, we can do without it. It's not.
Oh yeah, exactly.
Do people have it? Okay, yeah. Good. So go ahead and open your MS Stats Annotations template. And so this is just this. The only point of the Skyline document is that we all have. Yeah. So if you go to Settings, Document Settings, now you'll see that everybody should have bioreplicate and condition. Does everybody have that? That's okay, yeah, you get it. So this is, so MS Stats annotations doesn't have any targets. And the only interesting settings that it has are annotations and reports. And under it reports, you'll see MS Stats Input Plus. So that's the only point of this, of opening this document, is so that we get these annotations automatically added to our Skyline, so that everybody's on the same page. So I went to an NIH meeting organized by Steve Carr, who's here at the Broad Institute, and Rudy Aebersold, where we talked about what should people have to submit with their research to get it published. And I said, oh, well, if you're working with Skyline, it should be a Skyline document and your report templates. And then that made me realize that we should make it possible to include report templates in your documents. So now you can, that's one of the document settings. So the document settings, we have annotations, group comparisons, which allows you to do some rudimentary stuff like what you can do in MS Stats. So we're just going to ignore that for this course because we're going to be using MS Stats instead. And then you can have reports. So that's what document settings are. And we just opened up a file to get us annotations and reports. Okay. And we'll look at the reports later. I assume that if you took the session 1, you have some experience with Skyline reports. Certainly you should have at least opened up the document grid, which is where you can look at and edit reports. And we're going to open up the document grid in a second. But there's also, so yeah, that's kind of an interesting settings. If I'm in these settings and I look at this report, if I look at the annotations and I want to see, well, what is this bioreplicate condition? What are those annotations? I can click edit list, and then I can edit bioreplicate, and I can see that it's a text annotation that applies to replicates. And then similar for condition and reports. But if reports, it's like, how do I figure out what this report is? Anybody know? How do I figure out what's in this MS Stats Input Plus report? There's nothing to click here, which is probably a mistake, but go, yeah. Yeah, so we have to, so it's this just allows us to include reports that get defined in export report. So here's that list again, and you can see MS Stats Input Plus shows up in it. And then here I can do Edit Plus, edit reports. Click on this, and I click Edit, and then it will show me, okay, this report has these columns: protein name, peptide sequence, peptide modified sequence, and I can edit it. But we don't want to. Yeah, I think there. I just was looking through this. I think it's things like we added precursor charges, and we added some, or maybe it's just the MZs, product MZ, precursor MZ. We added some more information. If you have MS Stats without Plus, you can look at it, and they're really very similar. It's just adding some fields that maybe MS Stats doesn't use, but we'd like to have in the report anyway, just for diagnostic information. So okay, we'll come back to this. Now, actually, what we really need to get everybody doing is opening this big, massive file with everything. So now go to File Open, and we're going to open the Brooder. So and then you go to DI Pub Brooder, and here is, so we've got our Brooder tutorial.sky. Does everybody understand what a .sky.zip file is? Who does any? Raise your hand if you don't understand what a .sky.zip file is. Okay, there are a few people. So, a .sky.zip file is just I'll go open that template one. It's a zip file, so you can open it in Explorer and look inside of it. You can see it's got the .sky.view and a blib file. So this is, and you could, as an exercise for later, go ahead and try to create a .sky.zip for your Brooder tutorial. And all you have to do when you have it open is go to File, Share. And that's because a Skyline document is actually kind of a Skyline project. It includes a bunch of different files. So if you want to share it with a friend, don't just send somebody the .sky file. What you want to do is File, Share. You'll get a sky.zip and you can give them that. And so when you're up on the support board asking us questions, we're going to say, use File, Share and send us a sky.zip. So that the template file, well, let's open up the template file. Let's go File, Open, and I'm not right near it. Documents, pub, Brooder. Okay, so there's this Brooder template. Let's open that. So this is just, it takes a little bit to open, but it doesn't have any data imported. So it's pretty quick. It's basically that same template that you created yourself with 350,000 transitions, IRTs at the top, a whole lot of peptides, and the decoys. So this is me creating exactly what I walked you through creating yesterday. And then if you look at that folder now that I was in, how did I get? So I opened it from this Brooder 2015 folder. If you look at that, now I've got, I opened it yesterday. Every time I open it, I get a new folder with the files extracted into it, right? So it's kind of a nice way of saving a state that you can then go play with. Okay, so let's open the big thing. File, Open. And we have to go back up to Brooder 2015 and just open brooder.sky. Okay? Everybody there? Go ahead and click open when you're ready. And that has all the 24 files in it, and it will take a little bit to open. Any questions? No questions? I didn't just thoroughly confuse you all. So yeah, so actually, well, I'm gonna get access to while we're waiting. I'm gonna get back to having access to my remote machines where I ran the command line. So if I go back to that big machine, that machine that had 48 processors, and I ran all the processing there, then oh, that's a different one. So we were looking at the Brooder folder here. So I remember I ran an import. This is my log of my import. In the raw folder, I now have a folder that has a full processing with PDFs that I generated with R and everything. I also have a .sky file there, which I should be able to just double click and open. Skyline Daily. We're very close, so it should be quick. I hope. So this computer is in Seattle, so it should really be able to upgrade pretty quickly. So I'll get the latest Skyline Daily. I have really no idea what version of Skyline Daily is installed on this computer. I guess I'm almost. Does anybody have the Brooder.sky fully open? Yeah, okay. I'm almost there. I have a lot running on my computer. I might want to close some stuff down. All right, so here it is. So now it's, yeah. So there we are. I'm looking at my IRTs. Who still needs time to get Skyline Daily open or to get the breeder? Okay, so I'll go back to here where I now have Skyline open again. So I'm gonna open brooder.sky on this machine. And it takes even a little time to open on this machine, but it should go pretty quickly. But that's the fully processed document with the mProfit model. I could just then export a report from here. But we'll come back. So, okay, so hopefully everybody still has it open now? No? Oh, well, you're using a Mac, so you know, yeah. Okay, so let's take a look at, does everybody have the IRTs selected? Okay, so I'm gonna grab this retention time window to look at it. So you can see these are 24 runs, all imported. How do people feel about our IRTs? Did we do an okay job of getting IRTs? Yeah. What's the expectation? Each one of these colors represents a peptide. There's 11 peptides. Can anybody see anywhere where a peptide you're like, that probably is not the right thing? No, it looks great. Right, 24 across. They did a great job of collecting their IRTs. So that matches our expectations. If their chromatography were perfect, we'd expect a perfectly straight line going across. If we want to see it more, this is actually showing us a top-down view of the peak and its width. But if we wanted to see more of a line graph, you can. I changed it so you can now. If you switch so currently we're saying we want to see all values, but if you switch the values to I just want to see the retention time, then you get a line plot. You get maybe, how straight are those lines? Those are the peak apexes, getting rid of the information about the peak widths. Yes. Do you have that? Or what? One peptide missing? Oh, no, the line. Okay, that's not missing. Okay, so that's just you. What? Okay, so there should not be anything missing in this one. Here. So I must have turned off selection. So Skyline will show you which replicate is selected based on, so if you click these tabs, that's Skyline sort of showing you which tab is active. And and it works both ways. So that's one of the nice things about Skyline is these graphs are very interactive. And I can see which tab is selected here. I can also go over here and click on one and say, oh, I really want to see that one. And that will switch me over there. Okay, so I can bring these graphs out, and if I double click on their titles, they pop back into the window. And then if I want to, so now I'm going to bring this one out and I double click on its title and it will pop out at a sort of normal size. And now these are the peak areas. And actually, I have something going on with the labels, and my quick fix for that is just to select another protein and then select back, and now I can see all the labels. So what are your expectations here for peak areas? Do we expect anything? We have a bunch of different samples. Do we expect them to be different in the samples? So you can see that the acquisition scheme is sample 1 and then 3 replicates, sample 2 and then 3 replicates, sample 3 and 3 replicates. What do we expect of the IRTs? Well, I certainly went in hoping that I would see peak areas that just went straight across too, right? Because they're injected standards. Like what, I should be injecting them at a constant concentration, and there's a lot more variance here than I was hoping to see, expecting to see. I mean, it seems to impact some peptides more than others. This brown thing, seems to be very sensitive. Let's see, where is the brown peptide? Let's take a look at the brown peptide in retention time space. So you can see that it's the latest diluting peptide. Right here, it's the one coming out at 100 minutes. So it seems to be extra sensitive, but other things are going down too. Like here, everything's going down here. What's going on with that? Okay, so now another important thing to look at is okay, so we're seeing, does anybody know, were these collected in this order? I have no idea, right? So, what maybe there's something happened to the instrument, and boy, these all go, everything goes down toward the end, or maybe this was a bad run and that something broke. But we'll get some new insight if we look at the acquired time, because acquired time actually is really an important factor in mass spectrometry. Yes. Yeah, Skyline by default, if you import a whole bunch of files, it's just going to order them by the nomenclature, or by these names basically, or by the order of the file names. So we just selected a whole bunch of files and imported them. The Skyline will order them in that. You can totally change that. You can go to edit, manage results, and here we could just we got up and down, and we can move things all around and change the order. That's called our document order. So the other thing I want to look at right now is the acquired time order, and you can do that just by going right click, order, and so here's document order, which is what we've got, and we can also do acquired time order. So we can change the document order. We cannot change the acquired time order. That's just reality. So now what do we see? So what? Yep, we see. Wow, there is quite a bit of variance in this brown one, the one that comes out last, and this is the order, right? And so, are we happy with that order? Do we get a warm fuzzy feeling, if this were the order? Like, what were people hoping to see in terms of the order? You're at a statistics, you're here at a statistics thing. You should have some ideas of what's a good sample order. Yeah. So if this were really the order, this would be terrible. Like you'd be like, what did you do? This is this is where talk to a statistician before you collect the data, because you can't show up at a statistician and say, this is the order I collected them in. This is completely like a really logical, wonderful order. And what they want is they're going to want you to block so that you collect all your replicate ones together, then all your replicate twos together, then all your replicate threes together, so that you have a full experiment. So if something goes wrong, you just throw out that whole block, right? So and then they're going to want you to randomize within the block And why do they want you to randomize within the block? Because run order matters, and if you don't, then run order can become a confounding variable, right? You can end up just, like, wow, it's like, I see this effect. Well, if this is because your instrument kind of broke, then now all of a sudden, you have this effect that has nothing to do with the biology. It's just your instrument. So let's go back to acquired order. So here we're actually kind of happy with the acquired order, right? It's like they're not going 1, 2, 3, right? These are the first. This is replicate 1, and they've gone 2, 6, 1, 4, 5, 8, 7. We think that, and 3. That seems kind of randomized. And then even better, the next one is randomized in a new order, right? It's not repeated 2, 6, 1. It's actually, when we get out to R2, it's 4, 8, 6, 1. So, and it's possible. I know that Olga told me she consulted on one of these papers and forced them to do randomization, go back and recollect the data randomized. But so let's switch back to document order and select this one. So everybody switch back to document order and click on this one that really drops down, that we're like, whoa, did the machine break? So select that one. Everybody have the line on that? Okay, so now right click and order by acquired time. So where is that one that's really low? That's the first one. So maybe the column wasn't conditioned well, or there's like, maybe this is really an artifact of how the instrument was being run at that time. It's the lowest thing. It's the first one. We can kind of see this curvature going up. So it might be that they were actually that they should have done more work to condition the column, and the column's not really even fully conditioned until they get out to here, or something, right? So yeah, we're just by looking at the IRTs, we can learn interesting things. We definitely see that if this was the only thing that was changing, well, really the job of the IRTs is really just to be stable on retention time. So they don't need to be totally stable, but we can certainly learn stuff from that. But yeah, so again, we saw this. So we're not seeing any sort of order pattern. The only interesting order thing that I see is here. I definitely get nice feeling that, okay, they randomized. And so what that, I think, tells me, if I go back to my document order, my logical order, is that there's some sort of sample handling thing that's going on here, right? Because it really only affects 6, 7, 8, right? But it really does affect 6, 7, 8. So 6, 7, 8 somehow, like if these were subjects, biological subjects, I'd be like, whoa, hey, this might be a great biomarker, and it's really probably just some sort of sample handling artifacts. Okay, so yeah, great, interesting things you can learn just from taking some quick peeks at the data. Let's put that back. Yeah, and all we're looking at are the IRTs. Let's go and look at that first peptide again. And let's go to view, arrange graphs, tiled. Oh, I didn't want to do that. Don't do that. That's way too small. But if I had a bigger monitor, so this is where you get to go make the argument, I really need one of those 37-inch monitors and wrap around screen. The Buck Institute that now teaches one of these courses, they were the first place I went where they actually had 3 monitors, and they just stretched Skyline over all 3 monitors. Because Skyline is really quite fast. Actually, if you click on this, you can see that Skyline updates all those graphs pretty quickly, but they're really hard to look at it. So let's go view, arrange graphs, grouped, and we'll just say 6, and we'll let Skyline figure that out. And we'll actually make it in document order and distribute graphs among groups. So get to that. We're going to try that as an arrangement of our graphs. Well, so grouping, I would tend to think about, like, why did I choose 6? Because I have replicates of 3. So that's going to give me the ability to look at, hopefully, what I'm hoping is I'll get 1, 2, 3, 1, 2, 3. And because I'm using distributed graphs among groups, that means I can kind of see 2 subjects, or not two concentration points at once, or time points. This is a time series, I think. So it'll allow me to see 2 time series at once. So let's click OK. See how that, yeah. So that's how Skyline lays it out. I'm going to give it a little bit more room by squeezing that a bit. And then now if I go up here into this replicate view, I can select the first one and then go 1, 2, 3, 4, 5. And now I'm looking at all the replicates for sample 1 and all the replicates for sample 2 at the same time. And if I want to look at all the replicates for sample 4 and sample 3 and sample 4, I can do that same down arrow, 1, 2, 3, 4, 5, 6. Now I have another set. Many times people have asked for a keyboard command that just sort of like moves you back a layer for all your tabs. But so far you have to. The other thing is you don't. So there's this replicates thing that drop down here. If you press escape, Skyline will. I guess if you click on the protein. Now, when the focus is not in that replicates view, you can use the control key and do control up, and that will also change which tab is selected. So if I want to see 5, 6, I can go 1, 2, 3, 4, 5, 6, just with the control up and down. Okay, so yeah, now let's look at them one at a time. That looks pretty nice, although, certainly, oh, that's retention time. It's not super stable in retention time. And there's some jitter over the, so this is, which order am I in right now? Anybody know? Actually, I'm going to also get rid of the legend here because I've got other legends. So right click and remove the legends so that you can see the chromatograms better, because I have legends over on this other side too. So is this really jittering retention? Or again, we can right click and order by acquired time, and then we can see, oh, there's just some sort of, there's still some jitter here, but there's just drift. And maybe we switch back to, yeah. So let's go ahead and switch back to all so we can see the peak widths. And now we're much less concerned about this kind of work. When I look at things, peaks basically overlap, and I'm not really worried about it. But you can see that there is some drift going. And actually, because we have IRTs, we can right click and we choose show Bruder assay score, which is the IRT value. Whoa. I think we then have to choose a peptide. So now this shows us the times aligned to IRTs. And actually, you see that there was a drift this way. Now it's really quite straight across. Maybe a little bit. So that's just, rather than showing IRT, and you can see that all the peaks are like right on top of each other. So that's we're no longer looking at retention time. We're looking at IRT score space, and all of the predictions are going to be just like right along. Right, the prediction is now 117.5, which is just the IRT score. So yeah, so here, wow. We're using IRTs, right? And so let's keep looking at these. You know, this is one of the ones that if I do Shift F11, you know, there's nothing else I could have chosen here. You know, we kind of think this is a terrible, because what am I basing my, well, I have a Y10 and the Y3. So basically, and maybe the Y, and maybe the B11. Whoa. So that's all that's really co-alluding here, and that's what I'm calling my peak. But at the very least, I'm really consistently picking the same peak, right? Doesn't look anything like what I'm expecting for my library, and I've got about P0.44. So probably I don't really like that, but yeah. So you can see that things get chosen pretty consistently. And I think we're going to find places where we see interference. Yeah, like here. So and this is you know, our worst fear about interference is here we're not getting so much interference. We're getting a little bit from this thing. This other thing is caused by, what is this caused by? What is this? What's this thing sticking up here? What causes that? What? Is it chemical noise? Is it just like the well, what? Yeah, what in the matrix? It's another peptide, right? So and just as the peptides we're targeting have these really consistent properties of, hey, they show up at the same retention time, well, that's the same of other peptides. So if I'm getting interference from another peptide, it's going to show up pretty consistently and cause me interference a lot, but also it's not perfectly consistent, so it's kind of moving around. Here it caused me less interference, here's it caused me a lot of interference, less interference, more interference, right? So that adds a lot of variance to my measurements, and especially if there's change happening, these things might not change, or they might change really extremely. That's what we saw with the MS1. So we've been looking at, I've been showing you some plots where it's like, oh yeah, I think I can see because of the dot P's and some separation that there's probably some interference going on. And I've said, you have no other choice. With DIA, we can go, yeah, okay, we're gonna get rid of this Y6, and we can go look for other transitions that would be better for that peptide. We can choose we can keep trying transitions, because what we got them from is a fixed artifact. So it's just our choice. We chose these 6, and in a lot of cases, those 6 are doing great. We're a little confused by why is there no Y10? We're expecting a lot of Y10. So that's potentially not our greatest match either. Here again, super consistent, right? This is a different peptide. It may not be close to, we get a little bit from it. Mostly we seem to be chromatographically separated from it, but it's a concern, yeah.
If I don't have an assay library, but I have like another kind of a calculator, that also normalize the times.
Yeah. I mean, if you have, yes, you're going to you can normalize the retention times to IRT. You didn't have so again, these are equivalent, right? If you have a library built in Skyline, so we used an assay library. You could have built it for yourself. So this is just how Skyline, and in fact, when you take an assay library, Skyline, in order to use it in Skyline is building a spectral library and an IRT library. It's kind of faking, like we build the artifacts and fake Skyline out and pretend that we built them the other way. Yeah. Yeah, I mean, that's what I would like to do, is go and say, so I definitely, you know, if I were doing, and as we've been talking about, there are algorithms that are being developed that will automatically do this removal. There's one that was developed by Jake Jaffe's lab over at the Broad Institute, and Brian Searle has his own. So ideally, what we would do is we would do all this, and then we would run an algorithm, and it would notice a bunch of these things and do this, what we're going to do manually. We say, hey, that Y3 looks problematic. And now we could just select it and delete it. And then, hey, now we have no interference. And so that's what we're talking about in terms of, and if we really wanted to have 6, we could go look for more. But I mean, I think at this point we have 5 co-eluting ions. You know, we're pretty confident that we've got the right thing, and we can get better quantification off that. The trick is that I can't do this for, you know, 53,000 peptides. There's no way I'm going to go through all these manually. But the nice thing is, Scott, anything you're interested in, so you're not going to go through this methodically and look at every single thing, but anything that pops up is interesting, right? You run your statistics and you're like, oh, I found the really interesting things. That's where those slides I've been showing you, like, wow, look at the statistical difference among these peptides. And you go like, yeah, those are, you know, p-value of 1 to the -7th. And then we go look at it, we go like, yeah, but maybe there's some interference, and maybe, you know, and so it's very easy once you decide you're interested in, I think FF, you know, VG is a biomarker. And then you go look at it and you're like, oh, well, there was all this interference, I better retry that. Yeah. Yeah, you do your, so, yeah, and the people are working on all kinds of data QC algorithms. We're working on algorithms to get rid of this. So, I mean, the important thing, and part of why I'm showing you this, is like, this is totally usable data, and in fact, you know, quantitatively, we showed in the Navarro paper that Skyline behaves very similar to OpenSwath and Spectronaut, and, you know, and the other algorithms. So we're all dealing, you know, statistics are made, you know, actually a member of Olga's lab was the person that said this, I loved it, is like, we're trying to find signal in noisy data, right? That's what statistics is about. And the more you know, so even with this noise, you can still find interesting things. It's just a lot harder, right? It's like listening to music with static. You know, you can still listen to music with static, but wouldn't you like to have clear music? So the more you can do to clean up your data, yes.
I want to pick up on those comments. A really good one. There's I think it's necessity to do the manufacturing of component knowledge.
Absolutely.
Right now, the workflow, as far as I included in my slow mind, is that we do the statistics and then we do it cleanup. At least that's what you suggested.
What I'm suggesting is you can do the statistics and then you don't do a cleanup. You can then go and check your answer.
Yeah, it's true. So what's the perspective to have a systematic cleanup of 50,000 peptides?
Yeah, absolutely.
Now, what's the perspective? Is it going to be a Skyline integration? Are we going to?
Yeah.
For now, would we resort to an external tool?
Yeah. So at this point, there are external tools under development.
Do you have to say their names? Or?
What? Yeah, actually, Avantgardia is the one that's going to be presented at Avant-Garde. Yeah. It's gonna. You can go look at the Skyline user group meeting. Sebastian Vaca is going to present it. I'm not sure, is it Basa or Baca? No, I guess anyway. So, going to present at the Skyline user group meeting, and we're integrating some of the ideas that Brian Searle mentioned, and so anyway. But all that said, yes, if I imported, and I did this at the ETH course, I just imported the data as it was done in OpenSwath, and OpenSwath kind of just gave you a bunch of peak areas. You see these same things are happening, and so yeah, you can rush past everything to peak areas and do statistics, and you're just doing you're missing a lot of opportunity for cleanup, and you have noisier data, but actually, just statistically, without any cleanup, we know that this is less noisy data than MS1 extraction. So the thing that everybody's doing with MaxQuant and Mascot Distiller and that MS1 extraction, that is less noisy than these data. So you can see, it's easier to see these interferences because you don't get coelution on everything. I've shown you some examples of MS1 precursors where I have to really go, oh, it's the ppm, and you can see, and you have to come up with explanations. It's almost really difficult to even notice that it's interference, because so many peptides have the exact same, isotopic distribution, and MZs are like, the MZs match exactly. So basically, if you're isobaric at the precursor level, you just look the same if you elute at the same time. So it's easier to see the interferences, but just because you have an easier time seeing the interferences doesn't mean they're actually better. And you do have the opportunity to do these cleanup and get rid of them, but there are plenty of, like, if you think about this statistically, this is one of the strengths of doing protein quantification versus peptide quantification. If you think about this protein as a whole, we're going to get great quantitative statistics on it, because we've got, I don't know what is that, like 20 peptides, and maybe 2 or 3 of them have any interference at all that we can see, right? So quantitatively, MS Stats is going to have a great time with this. There's a little bit of extra noise. If we want to go to the peptide level and we want to actually have, like, a whole clinical assay can be based on a single peptide and a single transition as single peptide, just because that's the only thing they can get to fragment. If you want to do that, then you have to do a lot more work. But anyway, so I just wanted to do this with one protein. We definitely can't do it with all the proteins. Let's keep going to where we can get Mina a report. So wow, we looked at the IRTs in one protein, and we actually learned quite a bit, right? One thing, I do want to actually bring up one sort of advantageous thing about interferences and the fact that they are from other peptides. So, I deleted it, didn't I? If I undo my deletion, okay, so I'm looking at this. I talk about the chromatographic landscape. Is there anything but those two things? Not really. Okay. So this is part of the chromatographic landscape. And actually, if we were looking at MS1s and I did this Shift F11, I guarantee you there'd be more to look at. Right? So these data, despite not being as good as PRM or SRM, they are less. They are more selective than MS1. But anyway, when you have a sort of lack of selectivity, you can learn from this thing. This is another peptide, right? And so it's an anchor point. And so now, if this anchor point stays here and this thing disappears, I have seen presentations, very convincing presentations, that have used that fact to say, hey, my knockdown was successful, right? I'm expecting this thing to go away, and I prove it because it's no longer next to this other thing, right? And that can make it a little cheaper to prove than ordering a synthetic peptide. The other way you can prove it is to order a synthetic peptide and then they should coalute exactly, and you can prove a knockdown that way. But you can also just prove it because of an interference. You say, hey, especially, imagine if you had another thing right here, and then you're like, well, okay, if the thing in the middle goes away, then yeah, I really got rid of it. Okay. So Skyline has done a pretty good job of integrating things, right? I mean, in at least in these ones, we haven't seen any that are misintegrated, right? All the retention times line up really nicely. You notice that I don't see exactly the same, even with IRT normalization, there's variance, and I don't see exactly the same patterns. Some of them have some slope this way, some of them have some slope that way. So peptides are just not totally consistent in chromatography. Okay, so now what we want to do is we're gonna build a more sophisticated model, and we're going to use an M-profit model and repick everything. That's the best. That's going to give us the best results in terms of making sure all our peaks are well picked. And it also, more importantly, even if it doesn't change any peaks, it will give us Q values and the ability to make a false discovery rate cutoff, which is important to our statistics. So let's go and yes, go ahead. Yeah. So this is chromatogram peak picking. Yeah. Yes, RT. Yeah, and I actually try to call it centroiding. Peak picking is peak picking for mass to charge ratio. People say it, but it tends to end up being centroiding. So it's taking. So if you haven't heard the term before, people will say, "Oh, and then we did peak picking," which really just means that they took a profile shape and turned it into a stick, And so I try to talk about centroiding, and I use peak picking only for the retention time chromatogram peak picking. So let's go to edit, refine. And you did this yesterday, and it's going to take longer today because we have more data. So edit, refine, reintegrate. That came up nice and quickly, but then we're going to, and does everybody have something in here from your tutorial yesterday? Did you built something? What was it called? QE or yeah, there's probably a top one too. So okay, so click add. And now Skyline's got to go out and calculate all these peak group scores, and with, let's see, we've got 60,000 precursors, and then times 24, which is going to bring us up over 1 million, and then we have or is that, yeah, that brings us up over 1 million. No, it brings us up yeah, that brings us up over 1 million. And then we have 10 peaks per chromatogram. So we're like up to 10 million, or so it's got to do a lot of calculation here, and that takes a little time. So now was a great time for more questions. Yes, go ahead. Oh yeah. So that was passing my FDR for database searching. That with the DDA FDR. Yeah. So that was just like I'd run some DDA runs, and so yeah, there's several levels of false discovery rate here. So and there's a fair amount of error control. Like if every step of your experiment you allow more error, then you're just going to end up with a lot of error at the end. So that was just control of our library. So That's our starting point. We're trying to control the error in our starting point. And later, so the next thing we're going to try to control our error in is our peak picking, right? So okay, like, you know, we're going to try to do the best job we can possibly do on picking peaks. But if we see something that, okay, it was really low abundance and we're just really not sure that we were able to pick the thing, then we need to know, okay, that's not a value we trust. And then we're going to rely on MS stats what's the, is Mina here? She's not here. So I'm spacing on the term, but so MS stats will use this, like, what? Yeah, it'll use summarization, and so it will not use the value. So if it's got too low a Q value, we'll use statistical methods to come up with a replacement value. And so anyway, here we are. Is everybody facing the big thing? No, we got a really slow person again. Once you get there, it doesn't matter. As soon as you get there, just click train model, because that also takes some time. So we want to get to where we have a model for the brood data. So we got all the scores, and then we want to train them. And this is something that can happen all automatically if you're using the command line. So this is where I got kind of tired of pushing Skyline through big data sets, having to click the same button a bunch of times, and that's where I started switching to using the command line a lot, like I showed you earlier. So what it's doing is it's now learning this model, and it's got almost 1 million peaks at a 2% FDR. It starts at a 2% FDR, and it's doing this linear discriminant analysis, and it's learning weights for all these scores, and then it switches to a 1% FDR, and it loses some, and then eventually, when another round of learning does not increase this value, that's what just happened. So it's done. So it's 5 iterations done. I can't do any better than this. It then now is finished, and it's going to populate this with a bunch of data. And it's going to have a finished model. Right now, it's probably calculating the weights, which are the weights are already probably calculated. It's going to give us these percent values, which it has to do and analyze the variance in the values for. So yeah, I'm really pushing the amount of memory that I have on this. That's one of a key factor with this big a data set. And I've got a laptop, and I've got about 8 gig of memory on my laptop. Anybody who has 4 gig of memory on their laptop may really be struggling. Is anybody still working on the model? Yeah, still working on the model. Okay. If you don't have at least 8 gigabytes of memory, it's not going to work. So now we have a model. What do we know? What can people say about the model? Pretty good separation. There's not a lot of, so this means that we did a pretty good job of building the library. The library is, and I mean, this is what we expect. The library is built out of just DDA. There's no fractionation. So it's just DDA runs, all pooled, and then we built a library from that. So what this is just telling us is that for the most part, things that we were able to find in DDA, we're able to find again in DIA, right? So that's that, and there's going to be a pretty low false discovery rate. Because if you would see a higher false discovery rate, there should be another bump here of just a bunch of stuff that's essentially random. But there's nothing that looks like our decoys. It's just So if you imagine that there actually is a second distribution, it's going to be a very small distribution, because this just looks kind of like 2 distributions. I mean, if it were normal, it should be, more like this. And so the fact that we have some tailing over here is probably tells us that we do have some false discoveries. Yes, you had a question.
Can we keep the y-axis more?
Oh, x-axis.
Oh,
Yeah, it doesn't go any further. It doesn't go any further. I don't know. Can you?
Does RDS?
Nope. It's fixed. Yeah, that's adjusted for that data. If there was anything further out, you would see it. There's no, and actually, so this is actually a z-score. So this is a normal distribution. So it fits. You know, we make an assumption with M-profit that the data are normally distributed. The decoys look pretty normally distributed, and then we normalize these values so that that one is one standard deviation away from the mean. So out here, we're 4 standard deviations away from the mean. So really unlikely to be part of this distribution. Can you? Like, what can you do on this graph? Yeah, you can copy it. So right click, it will give you some idea of what you can do from it. So yeah, you can copy a metafile. Copy metafile is really nice for pasting into PowerPoint and Word for posters and things, because you get it's vector graphics. Yeah. Yeah, so let's talk about that. So one of the really nice things about Skyline and its models is one, you get this percent contribution, so you can see what's the most powerful score here. It's the same as we saw yesterday, this shape. Oh, actually, we saw it in the command line. That's where we saw it. So this is the same model that we saw printed out in the command line. We get to see all the graphics and everything. But this is the same model that we saw yesterday. So shape is the most intense. This is the best. Library dot product is quite good. And then this coelution count score, which is the original Skyline score. Retention time, not so great. This is, it's maybe 2-3% between these two scores. I guess if you add them all up, it's 4% on retention time. So and that's probably due to that wiggliness that we saw. So we might wonder whether that's really an artifact of the chromatography changing between the DDA runs and the DIA runs, or whether we could do better with a better algorithm for getting IRTs. So I'm going to go back and look at that myself. Signal to noise happens not to be a very good score. It's actually going the opposite direction as we expect, but really slightly. It's not, it's a very small weighted thing. So there's an algorithm, linear discriminant analysis, which is deciding these weights. And sometimes you'll see actually pretty big negatives. And that just means that there's some other score that's actually really close to collinear, like they vary very similarly. And so then Skyline will, or not Skyline, but linear discriminant analysis will go, well, okay, and it will separate them, and just like, so that can be an effect. And then mass error appears not to be very useful either. So, yep. I usually don't worry about it. It does, unless what I would tend to do is think about, is there I sometimes turn off this retention time difference squared, especially if I have a really big retention time. The problem with retention time difference squared is if it breaks out of some size. So if you're using like 30-minute retention time window or something, you can end up with retention times that are really far away, looking really great. Because Skyline will end up giving this one a positive score and this one a negative score, and then all of a sudden a negative score squared ends up being positive anyway. So I would think about whether more than like, oh, it's red, I'm going to get rid of it, more about, do you have a statistical reason to get rid of it? Another thing is we didn't use second best peaks. which we tend to use in targeted experiments when we don't have any decoys. So, and then if I use second best peaks, I usually get rid of the retention time scores because they're not really valid if you think about it, right? If you're allowing your first best peak, so they're not independent anymore because your first best peak occupies some retention time. And if it occupies the retention time right over the prediction, then you've got your second best peak is kind of forced farther away. So I tend to feel like if you're using second best peaks only, you should get rid of retention times. Yep.
Is that really like in academic experiments, is MTR checked Q values in purchase way, or people just using close to genetic standards?
I'm gonna let you ask that question again, but let's first have everybody name this Bruder 2015 and click OK, and then click OK again to actually do. That's going to take some time. It's got to actually adjust all the peaks. So go ahead now. Once it's first we see it takes time to working, and then now it's going through and adjusting all the peak boundaries, and that will take time as well. So now we have time for questions. Go ahead. Yeah, integrate all peaks, not only the significant ones. Yeah, because MS Stats will deal with the Q values, the assigned Q values. If you had a statistical tool that you were less sure of, or you really wanted to, basically choosing the significant ones allows you to make things missing values, like just completely missing values, and that can have an impact on the statistics. But MS Stats will deal with our Q values just fine, so we leave everything. Yes. 10 minutes. Yeah, people need a break, right? Okay, so let's take a break, and we'll come back here and finish this up, and then we'll start with the CelebSec data.